Put these notes on the cyclic process. You get out the pen for this. Okay, so just some review to make sure we understand. We went over this last time, but I want to just review it. Okay. Now, when we go, when we have a pressure volume graph like this, what's happening to the system's volume? Like the one on the far left-hand side. What's happening to the system's volume?
It's increasing.
Is increasing. So is work being done to the system, or is the system doing work? Okay, good. So let's label this the fact that the system is doing work. Okay. By looking at the graph, if I had the numbers for this graph, the values, how would I go about figuring out how much work it's doing?
Area.
Good. I would take this area. Okay. Now, this area, does that represent negative work or positive work as far as our equations go? Okay. That would be negative work because, again, it's expanding. All right. Now, what about the picture in the middle? Is work being done to the system or is it being done by the system? Okay. Work is being done to the system. So work done to the system. Is that going to be positive work? To the system. Let's just say the system. Get the eraser out here. To the system. So again, is that positive work or negative work? Okay, that's going to be positive work. And how will we calculate that work if we had all these numbers? Yeah, it's the area under this graph, and it's the area all the way down to the 0. Okay. All right. Now, how much work is occurring in the graph on the far right there? Good. How do we know that there is no work? Good. Okay, because delta V is equal to 0, so therefore there's no work. Okay? Because as rules implying, it's all about that equation, delta W. Okay? Now, what we're going to go over cyclic processes. So that was just a quick review. It says in a cyclic process, the gas returns, I don't know why it does that, the gas returns to the same states, to the same volume, pressure, and temperature. Okay? Since delta T is equal to 0, then that means delta, that's not right. That shouldn't say delta V. That should say if delta T is equal to 0, then what's equal to 0? Yeah, delta U is equal to 0. What equation tells me that? Good. Okay, that comes from the equation the change in internal energy is equal to 3/2 nR delta T. Okay, since delta U is going to be 0, what does that do to my equation? Okay, good. So it's going to mean that the internal energy is going to equal 0. So I got 0 delta Q plus delta W. So that's in a cyclic process when you go from the beginning all the way to the end. Okay? All right. So let's look at this situation here. If we go clockwise in a cyclic situation. So here's A. At A, there's a particular volume, there's a particular pressure, and there's a particular temperature that we would have to solve for, either be given. Okay. Now, when I go from A to B, what kind of work is that? When I go from A to B. Okay. That's going to be negative work. It's work being done by the system. How would I calculate that work? Okay. It would be area from here to where? All the way down to the bottom. Okay, all the way down here. So you got to include all that stuff to the bottom. What about when we go from B to C? How much work is done there?
0.
Okay, so that work is 0, so that doesn't count. Is that the same from D to A?
Yep.
Okay, D to A, that's also 0. But what about when we go C to D? How would I go about figuring out that work? Okay, that would be considered positive work. And how would I calculate that amount of work? Okay, that would be this area here. Okay, that would be that area there. So to get from A all the way back to A, how would I go about calculating the net work? So this is down here, this is positive W. Okay, this area here is positive W. How would I calculate the net work from going from the entire cycle from A back to A? What would that be? What's that? Good, but exactly. So it would just be the area in that box, right? So let me just go with a different color, green here.
So it's changing volume.
Say that again? Yes. Okay, so but on each part from A to B, the pressure is constant. So it's isobaric from A to B. So the pressure is constant from A to B, and then constant from C to D. And it's happening at different pressures. That's why less work is done in one situation as opposed to the other. Okay? All right. In this case, my equation, since my net work, is my net work going to be negative or positive?
Negative.
Okay? My net work is going to be negative. So in this case, my equation is going to be negative W is going to equal positive Q. Okay? So what this means is all the heat into the system becomes work being done by the system. All right? So it says so right there. Okay? So in the entire cycle, all the heat that's added to the system has got to equal the work being done by the system. All right? Now, let's look and by the way, that's called a heat engine when it does that. Okay? In a counterclockwise situation, okay, I go in the opposite direction. I go from A to D, D to C, C to B, then B to A. From B to A, is that positive or negative work? Okay, that's going to be positive work. And then from A to D, what is that going to be? Okay, A to D is 0. What about D to C? Okay, D to C, that's going to be this part, that's negative work. And then C to B, that's going to be 0. So to calculate the net work, what do I need to calculate? Yeah, just the area of this box. Okay? All right. In this case, what equation would I be using? Okay, because is more work being done to the system or by the system? Okay, more work is being done to the system. Okay, notice I got more work, there's more area under B to A than there is D to C. Okay, so there is more work being done to the system. So what equation would that be then? How, as opposed to this equation over here, how would I write the equation over there?
Positive work is negative.
Okay, so what that means is this. That means all the work done to the system becomes what?
Yeah.
Good. All work done to the system, all the work done to the system becomes heat out. Okay, now, on the example on the left, that's called a heat engine. This example on the right, this is called a refrigerator. A refrigerator, because we're transferring heat, we're taking heat from a warmer system, a colder system, and moving it out. Okay, so for this, we're just going to... Okay, so it's a refrigerator.
Refrigerator.
Yeah. Okay, I think I got everything we need to get from that part. Okay? All right. So I want to look at our first example. So turn to the back side, okay, and I want to calculate out 1 mole, or I want to calculate out this first part here. Okay, so this is a problem. This is the kind of problem you're going to get on your test. I guarantee you there's going to be a cyclic problem on your test. Okay, because it involves just about everything we need to do. We need to know all 4 of the thermodynamic processes. We need to know the first law. We need to know PV equals nRT. So that's why you always have some sort of problem like this, a cyclic problem. Okay, it says 1 mole of a monatomic gas undergoes the following process from A to B to C to D to A. Complete the following. Okay, first of all, they want to know, is it a refrigerator or is it a heat engine? And we know, but just by looking at whether it's clockwise or counterclockwise. So what would we say there? Okay, it's a heat engine. So I'm just going to circle heat engine because it's going clockwise. All right. Then it says complete the following. What is the temperature at A, at B, at C, and at D? Okay. So we've got 1 mole. So T sub A. Okay. How would I go about figuring out the temperature? Well, what would I use? What? Okay. We would use equation PV is equal to nRT. Okay. And so that would mean the temperature at A, so get out your calculators. Temperature at A would equal the pressure at A times the volume at A. Okay. Divided by the number of moles times the gas constant. All right. So what's the pressure? What's the pressure at A? According to the graph. Yeah, 2 times 10 to the 5th. I'm going to leave the units out just because I'm kind of... Okay, what's the volume at A? What's the volume at A? Okay, 1 times 10 to the minus 3rd. How many moles am I dealing with here? 1 mole, and the gas constant is? Good, 8.31. So that gives me a temperature of 24 Kelvin, which is very low. Okay, so that's 24 Kelvin. Okay, and now we could figure out all the other temperatures. Remember, using either this equation or we could use the other version of the equation. Remember where we always write this out, PV over nRT. Okay. The R cancels, so we always have P1, V1, N1, T1 would equal P2, V2 over N2, T2. Okay. In this case, when I go from A to B, what cancels out? Oh, you know what? These should be A's, right? That should be A. That should be A, and these should be B's. You don't have to change these if you don't want to. Okay. What cancels out? Okay. The pressures cancel because the pressure is constant from A to B, and what else? The ends cancel. Okay. So I essentially get this equation. The temperature at B is equal to the temperature at A times the volume at B divided by the volume at A.
So would that one be cyclic and isobaric?
Yeah, so it's the whole process is cyclic, but from A to B is isobaric. Okay? All right, so in this case, I would plug into my equation. I get 24K times 2 times 10 to the minus 3rd as the volume over 1 times 10 to the minus 3rd. What do you guys get for that?
48 Kelvin.
Okay, 48 Kelvin. Okay. So here's what I want us to do at this point. Okay, so I'm going to hit pause here right quick. So the temperature at C is what? What'd you guys get? TC, what you guys get? 24 Kelvin. Okay. And what about the temperature at D? Okay, they got 12 Kelvin. Okay. So here's what we're going to do now. Okay. We're going to go over how to calculate out the stuff from A. Let's go. I'm going to coordinate that part off. And here's what we're going to do. We're going to calculate the values from A to B. Now, because we're going from A to B, what's really specific about that? What do we know about going from A to B? Well, okay, but what kind of process is that? Okay, that's right. So isobaric. So we got to remember when we're solving an isobaric process. Remember, delta U, remember, is still always 3/2 nR delta T, but because PV equals nRT, it also equals what? Remember, 3/2 if
PV.
Yeah, P delta V. Okay, and because delta U or delta Q, for delta Q, remember that's 5/2. I kind of briefly showed you that that's 5/2 P delta V, and we also know that delta W is from A to B.
Is bagels on board?
Okay. Delta W, because it's negative P delta V, and because it's P delta V, we also know that that would be equal to nR delta T, right? nR delta T. Okay. So let's solve that then. So delta U, if we're going from A to B, how would I go about solving for delta U? Okay, what do I know to solve for? Good. 3/2 nR. Oops. And
say nerd for now on.
You can. nR delta T. Okay. So that's 3/2 times 1 times 8.31, and delta T in this case is always final minus initial, 48 minus 24, and I get a value of, what do you guys get?
10.9 to the 5th.
Okay. I think we get 300 joules.
Yeah.
Okay. Good. So we put that, Nick, can we put, we'll put that here for 300 joules. Okay. And then I can solve for delta W. Okay. To solve for delta W, what would I have to use when I go from A to B? What's that? Okay. So, yeah, I can go negative P delta V. Okay. Because if it's negative P delta V, what P am I going to use there? 2 times 10 to the 5th. Delta V, remember, is always final minus initial. So that's 2 times 10 to the minus 3rd. Okay. Minus 1 times 10 to the minus 3rd. Okay. And I know that value gives me negative 200 joules. Okay, so that gives me negative 200 joules. Now, delta Q, okay, I can say that's 5/2. That's 5/2 P delta V. Okay, but I could also say, I could also use this. Good. I could also use the first law. Delta U is equal to delta W plus delta Q. Okay. We already said delta U is 300 joules. Okay, delta W we said is negative 200 joules. So what does delta Q have to be then?
500 joules.
Okay, it has to be 500 joules. So that's what we would put in there, 500 joules. Okay? All right. Now, we figured out, so let's go over, I got to go to the next page here. Okay? So let's go B to C now. Okay, I kind of erased some of that, so, but you guys just keep it on your sheets of paper there, obviously. Now, going from B to C, what's a real easy thing to fill out in B to C? Okay, good. That's going to be equal to 0, because I know there's no work. Delta U, so from going from B to C, I could figure out delta U going from B to C using what equation? Yeah, it's always 3/2 nR delta T. Okay, so if I can calculate that out, and I get this value, and I'm going to go 24 minus, because of the temperature, I'm going to go 24 minus 48. Okay, I get a value of negative 300 joules. Okay, I get this value as being negative 300 joules. But because delta U, because I have delta W already, if I plug into the first law, if I have delta U is equal to delta W plus delta Q, what does, and I already know delta U is negative 300 joules, and I know that this is 0. Okay, what does delta Q have to be? Okay, it has to be negative 300 joules. Okay, so delta Q has to equal that, so I can automatically just plug in there negative 300 joules. Okay, now going from C to D means we got to do the same thing we did before with realizing that it's isobaric. Okay, going C to D, so delta U, C to D, I've got to use 3/2 nR delta T, and because I have some of these values, I'll just go ahead and tell you what they are. 3/2 nR delta T equals negative 150 joules. Okay, I would have to calculate out the work from C to D, and again I have these values, so I know that's positive 100 joules. So now that I've got the delta U and the delta W, how would I go about finding delta Q? There's more than one way of doing it. Yeah, I would just go to the first law. I know delta U is equal to delta W plus delta Q. Okay, delta U we just said is negative 150 joules. Delta W is 100 joules. So what does delta Q have to be then? Okay, negative 250 joules.
So each line is like a different thermodynamic process.
Yes, yes,
So
typically.
that's why they would use them.
Yeah. So delta U, negative 150. We said delta W was 100. And this was negative 250. Okay. So let's go D to A now. Okay, that's the easy one. D to A, what's easy on D to A? Okay, work is 0. Okay, and just like, so we're going to go D to A. Okay, we could figure out delta U using 3/2 nR delta T. And again, because I got these values, I'm just going to give that to you. That turns out to equal 150 joules. Okay, this turns out to equal 150 joules. So that's equal to 150 joules. According to my first law, what does delta Q have to be then? That has to be 150 joules. Okay, so let me fill out the top part since I got this from a different page. Negative 200 and 500. Okay, now going from A to A, right? We said that delta U, the change in internal energy, if you go from the same spot to the same spot, that always has to equal what?
0.
0. And does that work out for all of them? If I add up all of these, do I get 0? Yeah, I do. Okay. Delta W, okay, would just be this area. Now, if I calculated out that area, I can do one of two things. I can either calculate out that area, or I can just add these up. The negative 200 and 100 give me what? Negative 100 joules. Okay. And the delta Q, what I could do is I could just add all of these up, and that would give me a particular value. And what value is that going to give me? 100 joules. Okay. So now we can answer certain things like, what is the net work? Okay. Is the net work done to the system or by the system? Okay. So the work is done by the system. The net work is done by the system because it's negative 100 joules. Is the net heat lost or gained? Gained how much? Right here, 100 joules. Okay? All right, so that's how we go about doing these problems. So here's what I want you guys to do. Okay, so I'm going to, and the big picture is this. The work, the 100 joules of heat in, so let's write this down. 100 joules of heat in became what? Became what? The 100 joules of heat in became, good, 100 joules. Let's put negative 100 joules of work done by the system. Okay. Okay. So I think you guys can see that those end up actually